Just for fun. So differential calculus, I mentioned the other day, is the idea of a rate of change of a function. And most functions have a rate of change function. We call that the derivative function. And we'll just look at a few examples of those right now and kind of figure out our goal. So most functions have a derivative function. And that derivative function figures out how does the function change in any given point. Usually we think about change over an interval, so we got to figure out how do we reconcile change over an interval with change at a point. Did anyone have a chance to watch the video from the 3 blue, 1 brown guy? Yeah. What did you think about his animation about that change stuff? The idea, how can you have instantaneous rate of change? Kind of weird, interesting. All right, so we're going to ease into that right now. So I'm just going to start off with a super simple function. Let's take f of x equals 2x minus 1. Now, rate of change also means slope, right? So looking at that, what do we know the slope of the function is? 2. Yeah, so we should expect that this function has a rate of change function or a derivative function. So rate of change equals 2. So this thing has a derivative function. That's just equal to 2. And rather than write the phrase derivative function every time to indicate we're not talking about the original function, we're talking about derivative function, there's a few kinds of notation we might use. We might use f with an apostrophe of x equals 2, and we usually read that as f prime of x. So the original function, if it's called f of x, the derivative would be called f prime of x, if that derivative exists. Another notation we might see for this, because sometimes we write functions as, let's use a different color, y equals 2x minus 1. So sometimes people will write the derivative function as y prime. That's not a 1, that's a little apostrophe to the best of my ability, equals 2. And then from the idea of slope, do you ever see the symbols triangle y over triangle x? That triangle is the Greek symbol delta. And so that's read delta y over delta x, which just means find the change in y, divide by the change in x. So x2 minus x1, so be a 1 right there. And this change requires 2 points, but the derivative says you don't need 2 points anymore. We're talking about a single point, right? So that's no longer really change. It's what we call instantaneous rate of change. And the deltas turn into d's. So you might see the notation dy over dx. And each one of these, f prime, y prime, or dy dx, they all mean we're talking about the derivative function, the rate of change of the original function. All right, so I'm going to use each of those notations most days in the future. No matter what, in this case, the rate of change function is just 2. That's it. Because the slope of this graph is always 2, right? Let's make a quick graph of it. We just pick a couple points like 1 and 2, and let's go 1, 2, 3, 4 over here. Just a -1 in there. We know that this function starts off with a y-intercept of -1 from that part there, and then the slope could be considered 2 over 1. So we just from there rise 2, run 1, rise 2, run 1. So that's my best picture of this version of f of x. And we know the slope is 2. Now, straight lines are nice. They have the same slope all the time. Some functions do not. So let's look at, for example, f of x equals 4 minus x squared. What's that going to look like? Yeah.
It would look like an exponential function.
Not exponential. Exponentials have a hockey stick kind of shape. This one does not. This is parabolic. It's a parabola, however you want to say it. It's got a U shape to it. This one here, if you plug in 0, is going to have a y-intercept of 4. So if I start making a quick sketch of this sucker, let's go up 1, 2, 3, 4 there, and let's go to 1, 2 there. This is going to have the point 0, 4. And if I plug in 2 here, 2 squared is 4, 4 minus 4 is 0. I also get the point 2, 0. And this particular parabola is going to go up toward that and then down this way. So it's going to be upside down, concave down, parabolic shaped graph. And functions with the highest power of a square and no other powers besides x equals x to the first power, they're called quadratic functions. And quadratic functions are the only graphs that have a parabolic shaped graph. So parabola is the shape of a quadratic function. Quadratic function is something like ax squared plus bx plus c. There are many other U-shaped graphs out there in the universe. Parabola is just one of them. Exponential is like a hockey stick. We'll look at those later too. So here's my graph right here. Now the problem with this graph right here is at the top, like here, I'm going uphill, like if you consider that to be a positive direction. And on this side, I'm heading downhill, right? If you go from uphill to downhill, you got to hit a peak at the top where you're flat for a moment. Okay, so this has this point up here called a vertex. So at the top, I would say that at the very peak, the slope is 0. But you go the tiniest bit to the left, the slope is positive. The tiniest bit to the right, the slope is negative. Right, so on this side, m is greater than 0. On this side, m is less than 0. Other things I might note, if I'm at the top, it's not very steep if I'm a little bit to the left or right. But if I'm over here, this is much steeper than at the top, agreed? Right, we can see that in the picture. It's going to have a slope that's further from 0. So it's much steeper on either side there. So the slope is ever changing on this graph. At any point we pick, it's going to have a slightly different slope. Problem, right now, how do we find slope? Well, slope, again, is that change in y over change in x, y2 minus y1 over x2 minus x1. And if I want to know what's going on with the slope when x is equal to 1, that's going to put me right here at the point 1, 3. Just with 1 point, I cannot use this formula. Agreed? Not going to work. So we have to pick another point. So let's say I'm going to pick, something just a little bit on the other side of it. And I'm going to go close to it. So for my other point, just to test what the slope might be there, I'm going to say x is equal to 0.9. I'm just going to go a little bit to the left more. What's y? Well, for sure, it's f of 0.9. We can calculate that in a minute and see what value that is. And we're going to find the slope. Now I'm going to use function notation for slope. So that means I want to know what is f of 3. Oh, no. I value. What is f of 1 minus f of 0.9 divided by 1 minus 0.9. All right, whip out a calculator so that we can agree on what the slope is near the point 1, 3. I'm going to use Desmos. Graphing calculator. That's scientific, not a graph. All right. Anybody got slope? Come on, you guys, let's go.
I'll go about this one, and my computer says a great thing.
You don't have a calculator on your phone? What use is a phone without a calculator? Come on, it's more than just Snapchat and Instagram. What's that other TikTok? All right. So remember I talked about the benefits of function notation here. Download GeoGebra. No, what is this? Desmos graphing calculator your phone. It's wonderful. Anybody else have Desmos on their phone already? Hey, half of us. Cool. All right, get it on your phone or get it on your computer. All right. So I'm just going to type f of x. If I could type, here we go, equals 4 minus x squared. And then under that, I'm just going to enter my slope formula as a fraction. And I'm just going to type f of 1 minus f of 0.9. Anybody beat me to this yet? What's the slope going to be about there? 1 minus 0.9. I'm getting a slope of about negative 1.9. Anyone else get that? Got one nod. Aiden, how's it going? Not there yet. Do you know how to get the touchpad on there, the keyboard? Okay, yeah. Come on, play along. Fun. It's more fun. Watching me sucks. Doing it's more fun. Right, and just for fun, I'm going to put the point on there, and there's a couple of ways I can do that. You can type a point just by starting parentheses, and I could just do 1, 3. Now, that's because I knew 3 was the y value. What if you don't know 3 is the y value? Then you would just type 1, f of 1. And whatever f is, it's going to find the point where x is 1, which is kind of cool. So it finds the y value for me. Does that seem reasonable that the slope should be negative there? -2, yeah, I'll buy that. It's not -10, not 0. So -2 seems reasonable. So is that the slope at the point 1, 3? That's the slope near 1, 3. It's not at 1, 3. So I might play around. I might pick a point on the other side, like 1.1, x equals 1.1, see what it looks like on the other side. And I'm just going to leave that one there. I'm just going to retype it. Fraction f of 1 minus f of, this time I'm going to go 1.1 on the other side, divided by 1 minus 1.1, and I get a slope of -2.1 on the other side. Okay, so to the left of the point I'm interested in, the slope is -1.9. To the right, it's -2.1. Any guesses what it might be in the middle? What do you think? Might be -2. Now, -2 happens to be right in the middle of 1.9 and 2.1. Mathematically speaking, things don't always happen to fall in the middle. It depends on lots of other factors. Okay, so it's a guess, right? We don't know for sure, but it's a guess. So we're going to try and prove that guess through a little more experimentation. Now, we need more evidence. This isn't enough evidence. It's just we have an educated guess now. So some ways I could get more evidence is just by keep getting closer to x equals 1. So instead of 1.1, how might I get a little closer? Like 1.01, maybe? So we could try that. And I'm going to leave that one there. I'm just going to retype it so I can see my evidence in front of me. Don't have to worry about remembering what it was. Negative, I get a little closer to 1, and now I'm a little closer to -2. Okay. Are we for sure yet? It's just more evidence. We don't know for sure. So we could keep doing that. And for now, I'm just going to put some extra zeros here. So on the bottom, I'm going to go 0.1, and the top, I'm going to go another 0.001, -2.001. Put another 0 top and bottom. Eventually, what's going to happen, the calculator is going to run out of decimal points and just say, it's 2 as far as I can tell. But I think, or -2. I think we have some compelling evidence the slope is 2. All right, so that's just numerical evidence. It's not for sure. We can't prove without a shadow of a doubt that as close as somebody wants us to get to -2, we can find a way to get there. We just have a suspicion based on a bunch of pieces. It's circumstantial evidence is what it is. Okay, so is it guilty of -2? Not yet. So here we're going to try something a little more interesting. We let the second x value vary, true? First it was 0.9, then it was 1.1, then 1.01, then 1.001. So essentially, I've introduced a new variable here. Okay, and I'm not going to call it x because we already have x as our kind of general variable. I'm going to give it a new name. I'm going to call it a. So here's what I got right now. There we go. Notebook. Instead of 0.9 or 1.1 that we've been playing around with, we're just going to replace that with the letter a here and here and see what happens. Ready? Let's do it. So what is f of 1? There we go. So I'm going to take this f of 1 minus f of a divided by 1 minus a and see what happens. F of 1 means plug in 1 to the equation. The equation was 4 minus whatever x is squared. What is f of a? I'm going to put that in an extra set of parentheses. F of a will just replace x with an a. So that would be 4 minus a squared. That's an a, not a 9. And in the bottom, I have 1 minus a. And that's an a, not a 9. What should I do next? How about some clean it up? We've cleaned up expressions like this. 1 squared is 1, 4 minus 1 is 3. Okay, so I have a 3 minus, and I got to distribute this minus through there. So that's going to be a -4, and then minus negative a should be a plus a, and it's really a squared. And the numerator cleans up a little bit. What could I call the numerator? -1 plus a squared. over 1 minus a, and I'm just going to write this in reverse order. I'm going to write that as a squared minus 1 over 1 minus a. Okay, we have two options from here. If we wanted to reduce this, we could factor or we could use long division. I'd recommend factoring. We'll do long division later. How does the numerator factor? A plus 1? Yeah, it's a plus 1 times a minus 1. And a minus 1 looks an awful lot like 1 minus a, doesn't it? If we pick any number for a, like 3, 3 minus 1 is 2, 1 minus 3 is negative 2. Ah, so how is this sucker different from that sucker in general? They're just opposites, right? We change the order of subtraction. They're opposites. What happens when you divide a number and its opposite? 3 divided by negative 3 is what? Negative 1. 5 divided by negative 5 is what? Negative 1. Negative 10 divided by 10 is a number divided by its opposite is always negative 1. So this reduces to negative 1 right there. So this reduces down to the negative 1 times a minus 1. Now, what did I want a to be? I wanted a to be 1 because I wanted the slope when x is 1, not to the left, not to the right, but at 1. If I try to plug a equals 1 into this original thing, I'm going to end up with 0 over 0. Right? That's what I'm going to get. However, if I take this new version here, what happens if I plug a equals negative 1 in there? Or a equals positive 1, sorry. A equals 1. Oh, this should be a plus 1. Thank you. I knew something. I get 1 plus 1 is 2, but it's really negative. So this says, oh, negative 2. In this case, today, 0 over 0 happens to be equal to negative 2, which is the slope at that point. So I mentioned the other day, 0 over 0 is this intermediate creature that sometimes has a value. In this case, it's negative 2. Tomorrow, it will be something else, probably. That's the idea of calculus. So we're going to be developing these numeric and algebraic tricks to figure out what is the rate of change at a specific point, even though the original formula for slope will always fail at a single point. At a single point, it's always going to say 0 over 0. And then we got to figure out how to tease out the actual values. And that teasing out could be whip out a calculator and look for a pattern and where it goes when you get closer and closer to that, right? Wasn't the pattern leading us toward negative 2 as the answer? Circumstantial evidence is awesome. We just got some absolute evidence that says, oh, it's definitely negative 2. No doubt about it. And we're going to spend about 2 weeks beating up every function we can think of to figure out how to find its slope function. And every function's a little bit different algebraic trick to make it happen. Okay, so that's differential calculus. All right, let's look at integral calculus next. We'll do some homework problems.